Thank you very much. Welcome to Bristol Data Week 2025, organized by the Jean Golding Institute at the University of Bristol. My name is Patty Holley. I'm the manager of the Institute. And today we want to welcome you to Challenges and Solutions in Data Science in the Nuclear Industry, organized by the Southwest Nuclear Hub, a very timely event to discuss what solutions can be adopted by the nuclear industry now. We are named after Professor Jean Golding. She's a mathematician and epidemiologist, and she's the founder of Children of the 90s, an epidemiological study here at the University of Bristol. This study has been really successful, publishing over 2,000 scientific publications, and Jean still works at the university, a great example for all us to follow. If you want to hear more about Jean, we have a podcast, so it's called Bristol Data Stories. Here is the QR code, or you can find more information in our website. And we have quite a few more podcasts coming up. We also have a podcast with Seth Bullock, the director of the AI Hub in Collective Intelligence. So if you want to know more about Jean and Seth, please follow the podcast. So the Jean Golding Institute is one of the university research institutes. We support collaborations and partnerships in data science and AI. We manage the relationship with the Alan Turing Institute, the National Institutes for Data Science and AI. We also organize large events like Bristol Data Week, but also we organize workshops, seminars, and discussions across the year. So if you have any ideas for events, please get in touch. We also would like to help you publicizing your research and projects. So again, if you want us to help with that, please get in touch. And we also data science support, very importantly. So we have a team of data scientists and research software engineers that can be costed in projects, or also if you have, for example, you have a project and your postdoc, for example, has left and you have a little bit of funding left, and you need some support maybe in data analysis, please get in touch. We also have a team of PhD students that offer free data science and AI support with a help desk. Ask JGI at bristol.ac.uk is 8 hours of free support, and please get in touch. We also support academics across the university to develop grants with letters of support and environmental statements. And very soon, we're going to be launching a seed-con funding call with the Elizabeth Blackwell Institute for Health. So this call will be launched in July, and more information will be available in our newsletter. We offer training and capacity building. So for example, during Data Week, in the morning, we have been offering training. But also, we are very happy to talk to you about maybe bespoke workshops in your area of expertise. Data Week is a vibrant program of workshops, talks, panels, training sessions, and networking opportunities. If you want to see other events that you might want to attend, please, this is our QR code. And I would like to invite you, there's still a few spaces left for our public event to celebrate the university winning the National AI Award. On tomorrow from 5 p.m. at the Victoria Rooms. We have an excellent panel from across the university representing the research, the multidisciplinary research that takes place at the university. And our keynote speaker is Professor Sana Kargani. She was the former head of the UK Government Office of Artificial Intelligence, and she will give us an outlook of what are the most important issues now for the country. We'd love you to complete our feedback form. This is the QR code. We will also send the link at the end of the event. We want to know more about what you like, what was useful, how we can improve in next year. So thank you very much in advance for filling the form. And please connect. We want to hear from you. We want to support your work. So we are here to help. And like I said, we have a team of data scientists, research software engineers, and so it'd be really good to hear more about your research. So I'm going to stop now, and I'm going to pass to our host, the Southwest Nuclear Hub. Enjoy the day.
Thank you very much, Patricia, and good afternoon, everyone. My name is Tom Robinson. I'm the Research and Strategy Manager at the Southwest Nuclear Hub, and I will be hosting the workshop today. So firstly, I'd like to extend my thanks to the Gene Golding Institute and their Data Science Week. I think it's a great activity, set of activities across the whole week. So please take an opportunity to look at some of the other events going on for this week. So the event itself, we have 4 speakers on a variety of different topics around challenges and solutions in the nuclear sector. So as a brief introduction, in my mind, the nuclear sector is a really interesting place to apply data science. We have a really strange mixture, perhaps, of legacy facilities and new facilities. So we think about nuclear reactors that are currently operating in the United Kingdom. The most modern nuclear reactor that we have is Sizewell B, and that was designed in the 1980s and built in the early 1990s. So this is before a lot of digital tools and digital capabilities were available. And on the flip side of that, we've got a whole new generation of power stations being either commissioned or built or planned at the moment. So we've got Hinkley Point C just down the road in Bristol, which will be the first nuclear reactor in a generation. We've got Sizewell C on the Suffolk coast and the potential for small modular reactors, which will bring a new way of working with digital tools and techniques. And we've also got fusion power reactors in the pipeline with the STEP tokamak, so the spherical tokamak for energy production, planned in Nottinghamshire. So a real good mix of old and new, some challenges for data science in the implementation and the delivery, and now we're going to go on to talk about our speakers. So the way that the event's going to run, we're going to have 4 expert talks. We'll have a Q&A session at the end. So as our experts are giving their talks, please use the link that's been provided in the chat. So we've got a Slido link. If you can upload questions there, then we'll have a Q&A session after the talks where we can go through your questions and get an opinion from the channel. If you have a question dedicated to a specific speaker, please can you note that in your question? We can address that appropriately, or if it's a more general question to the panel, then please state so, and we can invite multiple commentary from our speakers. So without further ado, let's move on. I don't think I've missed anything. So our first speaker is Dr. Mark Bankhead. He leads the AI4Nuclear subgroup of the Nuclear Institute Digital Special Interest Group. He's a technical specialist in modelling and simulation with 23 years experience leading projects in atomic scale nuclear modelling and simulation, as well as nuclear adoption of digital technologies, including artificial intelligence and digital twins. So, Mark, if you'd like to share your screen, and we'll begin the talks.
Sure. Thank you, Tom. Thank you, everyone. Good afternoon. Switch into the presenter mode. Hopefully everyone can hear me okay. The audio's got a bit weird. Right, so today I'm going to give a short introduction to AI4Nuclear, which is a group that's aimed at establishing best practice in the application of artificial intelligence across the nuclear sector. Just before I start, I'd just like to advertise our big event this year. So we're actually hosting for the first time a summer school, which is going to be up at Daresbury Laboratories in Cheshire. It's a 2-day event aimed at either at leaders within the industry who are interested in working towards how they would apply AI within their organizations to solve problems. Or on the second track is actually aimed at AI practitioners, which could be scientists and engineers within the industry who want to new skill, I should say, in artificial intelligence methods and apply them to their day job. So we're very excited about this. There's information in the QR link provided, and we'll be very happy to see people at that meeting, which is in the 17th of July this year. Right, so moving on, I'll tell you a little bit about what the Nuclear Institute does around digital. So just in case you're not aware of the Nuclear Institute, so the Nuclear Institute's the nuclear industry's professional body. So whilst I work for the National Nuclear Laboratory today, I'm representing the Nuclear Institute as an individual member interested in promoting nuclear across its membership and beyond. And the Nuclear Institute runs a number of activities, one of which is what they call the special interest groups, or SIGs, which are groups aimed at really driving the industry forward in a number of key different areas. And for example, there's one on policy, there's one on newer applications of nuclear energy, and there's one on digital. So this has existed since around, well, various guys, it's probably since around 2016. The digital group reaches out to over 580 individual members. Now this list grows all the time, to be honest, so it's probably well over 600 now. And I think what's most remarkable about it is those individuals are drawn from well over 220 distinct organizations. And the digital group is aimed at advancing understanding of the applications of digital and data within the sector, and also to share case studies. Now, in 2022, there was an increased interest in artificial intelligence, so we spun off what became AI4Nuclear within the group as a subgroup. That's grown since 2022, so we now reach over 130 distinct organizations and 330 members. Now, there is some overlap between the two groups, but they're not exactly the same. So, in total, we're reaching quite a large number of individual members with our events and dissemination activities across a wide range of different organizations. Now, in terms of that makeup, the vast majority of those organizations are actually from industry. We have relatively few academic members. So academic members are not unwelcome, but it's just that we do tend to focus more on the industrial end users within the sort of topics and applications that we discuss. Now, the sort of activities which I'll tell you a bit about within AI4Nuclear is we organise workshops, which could be information sharing, and there could also be feedback sessions and information gathering sessions, training, which I've just mentioned. That's a new thing for us for this year, and our terms of reference is aimed at really producing industry-wide guidance, which I'll get into how we do that in the next slide. So basically our terms of reference is around development of industry guidance, and how we're doing that is basically by holding a number of meetings. These could be online or in-person events. There could be fairly large in-depth meetings of up to a day in duration. There could be shorter online meetings of 3 to 4 hours, and we gather our evidence either by within those meetings having workshop sessions where we capture the views of the industry members who attend that, or through the case studies that they present on how they're actually applying AI within the industry. And over the time we've operated, I think we're on meeting 9 now for the online meetings. So between them, we've probably had around 30 to 40 individual case studies presented, as well as we've held 3 in-person workshops where we've done quite a lot of information gathering around members, and from that we're pulling together the sort of the picture across the industry, and of course we're using AI to help to understand what's important within the sector from the outputs. So once we're in the process of, this is an iterative process to build this information, but probably about this year we'll have enough information to really start to put together what would be our first iteration of this guidance framework. Our route for that is going through NI's Foreign Policy Committee to endorse that guidance, and then we can roll that out through the Nuclear Industry Council to have that sector-wide endorsement. And that's what we're aiming to do within this group. I'll tell you a little bit about the individual members that make up about that group a bit later on. So just to give you a couple of examples, this is a couple, I've got a couple of case studies which have been presented at past meetings. And the first one is from PA Consulting. This is a piece of work that was delivered for Sellafield Limited, SL Comply AI. And this was sponsored by Sellafield Retrievals Value Stream. And the idea was, well, can we develop an AI tool to accelerate and augment specialist human tasks involving data? And this is what the problem they're actually tackling here was changes in legislative regulatory documentations. And for an engineer, keeping track of changes in legislation can be very time consuming. But the idea of this was to create a tool that can basically scan for changes in legislation and then extract from that which ones of which of the changes might actually impact on the individual's role and within the organization and the area of their responsibility. So this is used natural language processing with they were using some I think they were using some advanced rank-based techniques to improve the accuracy of that, and that was an extremely successful case study. So they reduced the amount of legal and regulatory text engineers need to read by 90%. So it was quite impressive, and Sellafield were very impressed with the performance of that. And more information can be found by contacting Derek at PA Consulting, who led the task. So it was a really excellent case study in showing just how already that AI is starting to impact the sector by creating tools that engineers can use day to day now. The second case study, probably more towards the academic side of things, is we've had a presentation from the university. This is Dennis Dachevich from Liverpool University. He presented around the idea of using artificial intelligence to basically take complex physics-based simulations of nuclear reactor performance and to produce high-fidelity AI-based surrogates of that that model that can be run on. And the idea was basically to take a model that can only be run on a supercomputer, which is not accessible to industry. Believe me, industry doesn't really have access to those sorts of facilities for various reasons, but they could be able to run that on a laptop. And some quite impressive results from this research, where basically they use artificial neural networks to predict the responses from the simulation and to basically train a surrogate model based on the outputs of the simulation that could represent the complex simulation. They've also been doing some other interesting work, which they're presenting, I think, next Monday at our next online meeting, which is where they're actually applying large language models to read the manuals of this software, with the idea being that it can produce an expert tool that can help, not just accelerate the use of these tools, but also to aid in the understanding and of the complex documentation that comes with these very complicated high physics-based simulations. So there's a number of I'll just say a little bit more about some of the activities that we've done. I mean, the first thing I'll say just on the left-hand side there is we have produced one white paper so far, which is the output from our first workshop, which is back in 2022. I think we published it in early 2023. This basically set out our approach for how we were going to operate as an organization driving AI through the industry. We've had a number I mentioned around the live and online events. We've had a workshop at first one was held at Daresbury, where we just basically did a lot of kind of high level capture around of the issues facing the industry, and I'll talk a bit about that on the next slide. We've had the online technical showcases where we present case studies like I've shown you there, and also as well as we bring information from cross sectors as well. So particularly through Innovate UK, we bring in examples where people have applied innovative uses of AI from other sectors and how that would then translate or inspire the nuclear industry to adopt these technologies for their problems. the workshops, and also sort of cross-organization engagement. So we've got a relationship with Alan Turing Institute, with BSI. We're establishing a link with the Open Data Initiative as well, with the idea being that we'll connect up with the various other cross. Another one I should mention as well. I mean, our last workshop was actually on large facilities. For AI research, where we had a presentation from Bristol University talking about their new AI supercomputer, as well as a presentation from UKAEA on the future direction of large-scale facilities for AI research within the UK. So that was, again, reaching out to other bodies working within innovation space in the UK as well as industry. So just to give you some idea of the sort of topics and sort of key, I suppose, factors that we've pulled out of some of our workshops, sort of challenges, capabilities, and opportunities here. So these are shaped from the three workshops that we've had. The first one was a general one around AI. The second one was around AI and standards, and the third one was about AI and regulation. And the sort of challenges that we see on the left-hand side of this slide are really the lack of skills. So the industry is very interested in AI, but we don't necessarily have the in-house skills to apply it. We have an aging workforce, so that is being addressed through various programs, bringing new individuals into the organization. Now, there's a fear of regulation, and we use terms like that within the nuclear industry group, because as individuals we could use quite strong, powerful words like this. But what we mean by that is there's a belief that AI can't be delivered within the industry because of regulation, but it isn't true. And the Office of Nuclear Regulation and the Environment Agency have been very supportive in helping us to sort of navigate our journey on that. But it's a challenge still that we have to overcome. And that lack of another one is a lack of interdisciplinary working. And I think it's recognized that, to get the true benefits from AI, we need to establish that across the sector. So in terms of the capabilities, what we see is one of the biggest challenges is the need for SWEP resources, or suitably qualified and experienced people, basically, in the AI sector. We need to increase the technical awareness in leadership roles, because I mean that's been a really big barrier to the adoption of not just AI but other digital technologies and other technologies as well. As leaders often don't have the awareness or the experience to be able to make informed judgments on the advancement of technology, and that sort of lack of knowledge within the industry as well. The few individuals who are aware of artificial intelligence, so they can't necessarily act even as an intelligent customer to bring that within their organization. But on the right hand side here, the opportunities that we've identified, that AI is a really powerful tool to preserve and share knowledge. Our next session on the 9th of June is actually going to be on AI and knowledge management, which is going to be online. Educating the workforce to have a broad acceptance of AI, that will help to sort of drive innovation. And another thing that we're tackling with this is we're using AI almost as a vehicle or a surrogate for encouraging innovation across the sector, and that's going to be a real focus of our workshop in July as well. Complement scarce high-value skill sets. This is something that we've picked out from our sessions about the idea. I think that example I gave from University of Liverpool is a perfect example of this. Is physicists are a very rare breed and very much in demand. So can we complement the skills by making their knowledge more accessible to others of more general skills, to enable them to do some of the work whilst taking the load off the few individuals who've got that really in-depth knowledge of those tools. And also there's an opportunity as well, to utilize our existing talent within the industry. So we've got quite large numbers of individuals who've got engineering and scientific backgrounds. They might not be familiar with AI, but they're probably quite good at maths. So we can look at utilizing those individuals through new skilling to bring in AI. And so that's really our whistle-stop introduction to AI4Nuclear. So, I think I've sort of given you some of a flavour of what we're trying to do around establishing the guidance framework for the application of AI within the sector. just really encourage those on the session today. If you're interested in helping the nuclear industry on its journey with AI, please get in touch with myself or Ray Chegwin, who's from Innovate Business Connect, who's acts as the secretary of the group. And we're more than happy to add you to the mailing list, and we're more than happy to welcome you to future events. Just on the right here, just like to thank the members of the steering committee who support me and Ray in the delivery of AI4Nuclear, particularly Naval Pinju, who's just retired from Momentum after many years of service there, Owen from EDF, Florian from the Turing Institute, Corinne from Sellafield Limited, Caroline from Innovate UK Business Connect, where she looks after AI for UKBC, Mike Martin from Rolls-Royce, David Smetham from Renuvo, who was previously at ONR, Carl Dalby, head of AI at NDA, Rob Akers at UKAEA, and thank you for listening today.
Great, thank you very much, Mark. Really, really interesting talk, and it's great work that you do through AI4Nuclear. I've been to many of your events and always learn a tremendous amount. So a reminder, if you have any questions for Mark, please use the Slido link that was put in the chat previously. I think we could share it again. I'll ask my colleagues to do that. And similarly, if you have any questions throughout the other talks, please use that link and we'll be able to come to those at the end. So we'll now move on to our second speaker. That's Samara Vazquez Perez. Samara is a data science with a background in engineering and experience in projects using machine learning for predictive maintenance and optimization, as well as projects involving data engineering and ETL design. She's currently working with Hinkley Point C, helping project delivery using data engineering and analytics. Samara also researches multi-energy systems coordination part-time on her PhD, and she's from Ada Mode. So Samara, if I can ask you to share your screen and we'll hear your talk.
Yeah, of course. I hope everyone can see that. So yeah, hi everyone. I'm Samara. I work for Ada Mode as a data scientist, as Tom just said. I've been with them for the last 4 years. And today I'm going to talk to you about a project that I've been working on for the last year, which is called the MET hazards, which stands for Extreme Meteorological Event Hazards, and how IoT has helped in this case. So yeah, so today I'll introduce you briefly to the concept of IoT. Then I'll touch briefly as well in the climate change challenges within nuclear. And then I'll go into a bit more detail into this project. So I'll give you a little bit of context, and then we can go into the details of it, what the data landscape was, what data pipelines were built, and then what the results and the conclusions were. So first of all, IoT, or the Internet of Things, refers to a network of physical items or devices that has a set of sensors, has got network connectivity, and that it can share and collect data. So these IoT devices can measure a range of things like temperature, like sunshine, radiation, like humidity, like building occupation, for example. And then when this data is extracted, it can be used to analyze patterns, trends, or anomalies. So on the figure on the right, you can see a standard IoT pipeline where there's a sensor network. So this can be what I was talking about, like temperature, wind direction, and sunshine radiation, which then communicates with a cloud infrastructure where the data can be stored and then extracted to get any insights. So the benefits of that is that it enables real-time monitoring, data-driven decision-making, which then can increase the efficiency of any kind of operation and also improve the safety from the continuous monitoring. So the challenges from climate change is the increase event, like extreme meteorological events, like droughts, like heat waves, like floods. And in nuclear in particular, heat waves pose a great risk because they threaten plant efficiency, because the plant can get overheated, and therefore there's some restrictions on how you can operate, which then can lead to outages. So when nuclear safety cases are defined, these are taken into account. But however, with the increase in frequency, these cases need to be reassessed on a regular basis. So in order to do that and to ensure resilience, there's a need for a robust data structure, and IoT offers just that in order to verify these safety cases. So I'll go now into a little bit more of the project I've been working on. So this project involves a total of 6 nuclear stations across the UK. And yeah, so as I was mentioning, the increase in temperatures and the higher frequency of extreme meteorological events, like the heat wave of 2022. So the UK sea temperatures that had never been expected to happen before, and in some cases within the nuclear stations exceeded the limits of the operating conditions that were defined before in the safety cases. So, and that was when that happened, and they realized they had to reassess the safety cases. They realized that there was no temperature sensors measuring the equipment that had to be verified, and also there was some monitoring externally, but there was nothing in detail other than just temperature. So therefore, there was not enough understanding of how these heat wave events were affecting this equipment, and therefore there's a requirement to increase temperature monitoring across the plants to verify their safety and the conditions and the visibility of the operation as well. So what we did is install a new set of temperature sensors to verify the safety of the stations, and then collect and analyze any of the historical data that was available to identify any hotspots or any sort of interesting information from the heat wave events, and then set up a short-term pipeline for the available data to sort of like digitalize it properly and put into a database, and then a longer-term pipeline including weather station data and the newly installed sensors for continuous monitoring. And then all of that was accessed in a dashboard so that you could see the insights. So when the project started, as I was talking about before, there was a lack of visibility in the key components that the safety case need to verify, and there was not enough temperature data anywhere really. So there was just external temperature and room ambient temperature, and this data, even though it was there, it had never been analyzed in depth. So in order to verify the safety case, some action needed to be taken. So yeah, so as I was saying, the data availability was just ambient temperature inside the rooms of the station, and then external ambient temperature from a Stevenson screen sensor. So to overcome these limitations, we decided to install a set of temperature sensors in the key equipment, and these were the stations that I've been talking about. So yeah, like as I said, first of all, it was the solution came from installing these data loggers. So these data loggers were temperature sensors near the key equipment, which then communicated with Bluetooth, and the data was stored in some form of database provided by the manufacturer, but then could be downloaded to extract some insights. And then on top of that, we also install an IoT board to create a weather station for like that continuous monitoring that I was talking about. So these two sets of data, I guess, then were fed into the two pipelines I mentioned before. So a initial pipeline for the historical data, and then a long-term pipeline combining the historical data, the data loggers, and the weather stations, which I'll give you a little bit more detail in a second. So yeah, so the first of the data pipelines was one collecting the cubicle data, the data loggers, and the historical data. So as I mentioned before, the data was downloaded directly to a laptop, and it was in CSV format. Then, because it was an initial pipeline, as I mentioned, it was processed locally with a Python script, and then that was uploaded into a database that then could be accessed in Power BI. So the second data pipeline is the weather station one and the longer term one. So the weather station, this IoT board containing a range of sensors, was battery powered and woken up every 10 minutes to collect the data. The board was equipped with a SIM card to avoid any sort of wired connection and internet connection. And then it communicated with a cloud environment using 4G communication. So the data was collected and packaged into JSON format, and then was received by Azure's AOT hub that then went into a data staging process. So again, Azure data storage was used, and then data processing happened also within Azure before it got stored in an SQL database that could be accessed for visualization later on. So I'll talk you through now the sort of analysis that we did into like the historical data and the data loggers. So this analysis was done to verify the safety of the operation. So it consisted of historical data that was already available across the plant. So this data was 5 years long, from 2019 to 2024. And then from the newly installed set of sensors, the data was collected throughout summer of 2024 to understand how the heat events were affecting the key equipment. So there was an assumption on how the difference between the external temperature and the room temperature should be, and by using the temperature loggers data, we could verify whether that difference also held with the key equipment, or if there was any trouble with it. So yeah, so we checked the temperature differences throughout time, and then we also checked. We did some correlation analysis and some log analysis to understand all the previous heat waves and the data from the summer of 2024 to identify any hotspots, as I was talking about earlier, and if there was any delays within external and internal temperatures. So thanks to having some data available within the plant and then installing these new sensors, the safety case could be reassessed and could be verified. And the conclusion was that the equipment was still operating within safe conditions, that there was a direct relationship with external temperature as expected. But however, from the already existing cooling measures within the stations, yeah, the key equipment could still operate within the safety limits. So as conclusions, yeah, so as I've been mentioning throughout the presentation, climate change poses challenges everywhere. And within nuclear, we've seen temperatures in areas that previously would have never thought were possible. And by making use of whatever data is available and installing additional IoT functionality, we can help improve safety and improve the operating conditions. So yeah, so in conclusion, there's a need to invest and develop more IoT capabilities like sensing devices, data pipelines that then can lead to increased advanced analytics and AI. So yeah, so all of this can unlock awareness of how this climate change weather events are affecting the stations, and then improve safety and improve the operation efficiency. So yeah, so that is the end of my presentation. Thank you very much for listening. And yeah, if you've got any questions, I'll be more than happy to answer them later at the end of the session.
Great, thank you very much, Samara. Really, really interesting project. I think myself and a lot of people will find that very valuable and want to know a lot more about it and what we can do on our own systems and our own challenges. So keep your questions coming in on the Slido link. We'll come to those at the end of the presentations. We'll roll straight on if that's okay. So our next speaker is Professor Chris Truman. So Chris is a professor of solid mechanics at the University of Bristol, and he works on structural integrity of nuclear systems, focused on particularly high temperature materials behavior and welding technology. He's a director of our very own Southwest Nuclear Hub. He's co-investigator on the SINDRI Prosperity Partnership project, and he sits on the EPSRC Strategic Advisory Team for Engineering. Chris has long-standing links with EDF Energy and has managed the EDF High Temperature Centre at Bristol for nearly 20 years. So a wealth of experience to bring to this talk, Chris, and we look forward to hearing what you've got to say.
I guess by wealth of experience, you're saying I'm old, Tom, but can I check first of all you can see my screen before I start talking?
Yeah, we can, yeah.
Okay, so thanks everyone. Before I move on from the title slide, let me just give a bit of background here. So Tom is right. SINDRI, that what I'm going to talk about today is work that's mainly been developed as part of the SINDRI Prosperity Partnership. So this is a very large EPSRC funded project, but industry led, and the industry is EDF. I should also say now, because otherwise I will forget, that a lot of the slides have been produced by Hugh Dorward, who is a PhD student coming to the end. So thanks, Hugh. And I've also taken some slides from other PhD students as well. So that's a sort of acknowledgement. Now, I'm going to start with what I've called the surrogate modelling vision. And I think it's worth just spending a minute or two on this because it sort of sets the scene as to what I'm going to talk about in the following slides. So if you can, I'd like your eyes to be drawn to the right-hand side to start with, where it says structural scale finite element. FE stands for finite element model. And that thing with the colours there is trying to represent a real plant component that you would find in a nuclear power station or reactor. So it could be a reactor pressure vessel, it could be pipe work, it could be a boiler. But the point is, it's very, very large scale. And components like that, operators like EDF need to convince are safe to operate. So historically, what we've done is we've used these continuum scale numerical tools like finite element analysis and some rather empirical based rules to try and convince the regulator that everything is safe to continue. What that's meant is there's been lots of conservatism. Everything's doubly safer than it needs to be, and we're not taking advantage of developments. And in particular, there's a real drive for physics-based models of material behavior. So these are models that are based on actually what's going on in the material, as opposed to basically polynomial fits. We want to include what's going on at the granular level of material, and that's the box on the in the blue background on the left hand side, primarily because lots of the key failure mechanisms, whether it be creep cavitation or stress corrosion cracking, originate and manifest themselves at the granular level. So in order to be able to make safety predictions, we need to be modeling at that level. Now, what you will see are the mesoscale model on the left and the full-size structural model on the right are linked by these boxes, surrogate material model. And that's what I'm going to spend a fair bit of time on, well, not too long, but the next few slides talking about to tell you what we've been doing. The other key thing to flag at this stage as well, by going back to this physics-based model, is it allows us to naturally look at the flow of uncertainties through our analysis, which is really important now because it gives us a better handle as to what's going on, and it allows us to follow sort of what we call damage tolerant frameworks. Now, this is a really busy slide, and I'm not going to go through it all at all. CPFE at the top stands for crystal plasticity finite element analysis. There are some equations in it, but I'm not going to go through the equations because nobody wants me to talk about those today. But the key thing is on the right-hand side. So at the bottom, you've got your what we call the randomized volume element, which is a granular level representation of the material. And what these crystal plasticity finite element models do is they allow us to accurately predict how that granular size, sort of micron level cube of material behaves under loads. And those crystal plasticity finite element models are based on clear physical principles. You know, there's a critical resolved shear stress on a particular crystal slip plane. You calibrate those models to the experiment. So that little copper thing on the left is a example type experiment, and you can make some really, really good predictions of material behavior. But it comes with one particular drawback. These crystal plasticity finite element models have lots and lots of adjustable parameters in there, 8, 12, it depends. There's different classes of models, but there's lots of parameters, and you need to fit to the experimental data to get those parameters. It's completely beyond the hope to run these crystal plasticity models at the length scales of the full component analysis, and we need to reduce the number of parameters to make these models workable. What we're really trying to simulate are the two curves on the left hand side. So I don't know who knows about sort of basic material behavior, but just to recap, the top curve, the stress strain curve, is what happens basically if you pull a material in tension, it loads linearly, and then there's a yield point, and then it goes, there's some plasticity, irrecoverable deformation, and if you cycle it around a loop, you get that cyclic behavior on the bottom right hand side. Now, this is not a talk about materials. What we're really saying here is that's how materials behave, and that's what we want to replicate with the proper material properties. Now, what I'm going to talk about mainly is a Gaussian process surrogate model. There are others available. In one of the earlier talks, we had artificial neural networks mentioned. The reason in this particular work we focused on the Gaussian process model is it's not black box. We have to convince people that what we're doing is safe. So we need open mathematics to demonstrate what we're doing is key. So the takeout points in my mind of a Gaussian process surrogate model are those bullet points there. And you can read them if you want, but Gaussian process regression is a non-parametric machine learning technique used to predict the output of a model or a process for a set of test data points X star based on a set of observed training data points. Each test and training data point is modeled as a random variable. It's a true normal distribution. Hence we can, well, I'll come to something in a minute. So the outputs of the crystal plasticity finite element model are used as synthetic data to train the surrogate model. We can include the statistical metrics of the microstructure in the randomized volume elements, such as average grain diameter, orientation, different parameters. And what that does is it allows us to feed through the uncertainties. And we're going to use functional principal component analysis when we need multiple output variables, such as the yield stress and the texture. So that's basically bookwork. So what we're doing here is this. When we develop our Gaussian process model, what we want is the figure on the top right hand side. So you will see the first time you look at this, it looks quite complicated, but what you've got are lots and lots of stress strain curves which correspond to the different statistical inputs of your little cuboid randomized volume element, depending on grain metrics and things like that. Now the beauty of the functional principal component analysis is that we can represent that complete suite of curves and all of the variances there by a mean stress and what we call the basis functions. So that's what the graph is on the bottom right hand side. We've got one mean stress and some basis functions, but the point that the advantage to doing it this way is that we naturally incorporate all of the uncertainties flowing through that randomized volume element. And we can do the machine learning regression to get those weights. So diagrammatically, this is what it looks like when we're trying to model the cyclic behavior of real materials on the right hand side, where you see the stress strain curve going around in a loop. The physics motivated input variables are on the left hand side, which is the accumulated plastic strain, the prior cyclic plastic strain, and the current cycle strain range. We can train our multi-output Gaussian progression model, and we can work out the weights of those basis functions, and we can reproduce what we want to reduce, but we've got a reduced number of variables. To show you how well this works, what we've got on this figure are two curves. We've got the red dashed line, which is the result of a full crystal plasticity finite element analysis going around many cycles. So we've got 20 shown here, where the graph shows the cycles 1, 2, 3, 10, and 20. And we've got our results of the reduced Gaussian process model in black. And you can see how well it reproduces the data that we want to reproduce. We can also look at the flow of the state variables as we go through, and here you can see on the left hand side is the prior plastic strain, and on the right hand side is the accumulated plastic strain. But again, it's to emphasize that the statistics of these things flow naturally through the process. So the uncertainty in the state variables does compound with each iteration, but we do have a full knowledge of what it's doing, which is important for the end. Finally, on this slide, so you'll see the by using this Gaussian model, we get the full variance of the stress strain curve as well in the uncertainty response. So what I wanted to come back to then is that's showing us that the Gaussian process surrogate model is accurately replicating the crystal plasticity models. But we can also, the beauty of it is because of the way of it's framed in terms of the functional principal component analysis, we can use it for as many output variables as we want. And another thing we might want to look at is the material texture. So what we've got here is a typical joining technique in plant is a weld. So you could have a pipe, which is the the top left-hand figure. It's joined together with an electron beam weld, which is a new welding process. If I look at the central figure, it shows the line of the bright colors is the texture plot going down through the weld, and you can see that there's different textures. They're pole figures on the right hand side. There's different textures in the weld and the parent material. Now this is exactly the point of why we're trying to develop this framework, because those different textures would lead to different material response, which ultimately will lead to different material behavior in our larger structural model. And we want to link all of this together to make sure that we continue to be safe to operate. So the same Gaussian framework applies to the texture as did to the cyclic behavior. So on the left hand side, we've got the texture. In the middle, we train the models in terms of the Gaussian processes, and on the right hand side we can make the same predictions of material behavior in terms of stress strain curves. There you go. You see there's different ways of doing this. I won't dwell too much on it, but we can represent the texture by a distribution function, a fully statistical compliant function, and we can make predictions of how it behaves, or we can use simplified approaches where we just basically label the orientation with a Taylor factor, and one is better than the other. Now I just want to finish off to go back to the beginning where I said the key point was we wanted to use these mesoscale models that are based at the in terms of microns, but we wanted to actually use those results to predict component level or structural level material behavior, and that's where these results link in now. So this is a diagrammatic representation of how we're starting to do this. So if you look at the figure, which is basically the test specimen, which has got the sigma sign coming out of the top of it, you can see that we can look at one of these randomized volume elements and represent only the randomized volume element by our surrogate model and link it in to the old style continuum model. And the way we link it is by mapping down the boundary conditions from the full model and placing them on our randomized volume element model, which I've just been talking about. So we're moving towards being able to do these full size structural analyses using genuinely physically driven mesoscale models of material performance, all in a manageable time period because of the adoption of the surrogate models. And we're also doing it in a framework where it's open and transparent what the flow of uncertainties through the whole process is, so that we can convince any regulators that what we're doing is safe. And that shows you where we are at the moment. So it's basically saying that these full size experiments and simulations are starting to agree with each other. So I've probably gone through a lot. I've got one slide of final thoughts. So what we've been doing is part of a wider general framework attempting to allow the accelerated prediction of mechanical behavior for different loading conditions, material model parameters, and microstructural parameters. Data science and machine learning methods are useful in optimizing complex models such as crystal plasticity finite element analysis, as well as for the emulation of complex models. The crucial aspect is propagating uncertainties through physical processes and length scales to allow probabilistic analyses of components. We can encounter trade-offs between explainable, interpretable methods and surrogate model accuracy. Models that perform better tend to have more abstract data-driven input-output variables. And the final point I made is the incorporation into full-scale models via multiscale approaches shows promise, and is key to utilizing the information provided by the meso models in real component analysis. And that's where this talk finishes today.
Thank you very much, Chris. A lot of incredible results there that you've presented. Am I right in saying that the expectation is that this will be published or made available through the Sindri toolkit?
You are absolute. A lot of the tools that we are developing are going to be open access through the Sindri toolbox. There are further challenges there to put it in a framework that is acceptable to all parties, but that is the principle of it, yes.
Great. So I guess everyone on the call today can look out for the toolbox becoming available and do some CPFE for themselves if they want to.
Yeah, they're very welcome to.
Fantastic. Well, thank you very much, Chris. Now we'll move on to our fourth and final speaker, Professor Andrew Davis. So Andy's the head of Advanced Engineering Simulation at UKAEA, which is the UK Atomic Energy Agency. The group has several core themes at the interface of physics, engineering, computer science, and high-performance computing, and is pushing the boundaries of fidelity and coupling of simulations to allow predictive simulation of complex phenomena that arise in fusion reactors. So, Andy, if you'd like to show your screen, we'll hear your talk, please.
Absolutely. So hopefully you can hear me and you can see my screen.
Yeah, that's right. Yeah.
Super duper. All right. Thanks, Tom. So I always come up with my slide titles, my titles of talks at the very last minute. When I've really written the slides, then I figure out what it's about. Then the title comes out. So this title spoke to me, which was, without data, you're just another person with an opinion. So it's obviously through data that we make our decisions. And this talk is kind of all about that, how it pertains to fusion. So just a bit of information about UKAEA, in case you don't know who we are. We were formed a long time ago, back in the 50s, really at the foundation of Britain's nuclear research programme. And the bit that really matters to us now is this bit here. So after 2009, the only bit of UKAEA that was left was UKAEA Fusion, which is at Culham, which is this bit down here. In fact, it's quite interesting to see how quickly an organisation can forget how it used to be a multi-site endeavour. So really, we focus on the delivery of UKAEA's fusion programme. So at Culham, we historically hosted two devices. We had JET, which sat in this big building up here. In fact, these two big prominences at the top of that building are specifically for radiation shielding doors to go up and down. JET, of course, is now, the project has ended. So we're left with just running, in terms of experiments, plasma experiments, the mast upgrade tokamak. So really, we exist to kind of further the UK's fusion dreams. We have a problem though, which is that if you want to rely upon experiments wholly to de-risk your fusion program, you're going to hit a bit of a sticky wicket, because the in-vessel conditions of a fusion reactor are brutal. We are dealing with extreme heat fluxes. So we often talk about entire power plant levels of heat being deposited at the bottom of the reactor on a component called the diverter. We have neutron fluxes in excess of 10 to the 15 neutrons per square centimeter per second. This is typically about 10 times higher than that of a fission reactor. These significantly energetic neutrons cause transmutation and radiation damage. They deposit heat. This results in temperatures in excess of thousands of degrees Kelvin. The plasma itself erodes first wall material when it interacts with it. None of this happens with strong magnetic fields. And it's an unfortunate truth that the only place you can find this load is in a fusion reactor. So until you've developed one to do your testing with that works, you can't really do the testing you'd like to do to de-risk it using a normal approach. Even more so when we think about how long these components have to last. We're talking actually about quite significantly expensive components. And for these things to last at an economic timescale, they have to last about 5 years before they're being replaced, which means they're subject to radiation damage of around about 200 dPa, which is displacements per atom, and certainly helium production in excess of 50 parts per million per full power year. So fusion really has done its design by iteration. This is a wonderful graph produced by a chap called Sam Wurzel from MIT. And this you can think of as Moore's law for fusion. So NT is the product of ion density and confinement time. So a dense plasma that you keep particles well confined versus the ion temperature. And this straight line you can think of as like Moore's law. So you can see that as time goes on, we get closer and closer and closer to these blue and red colored bits at the top, and this is the target, right? So as you get closer and closer to this number, well, in this case QMCF, or the engineering Q, how much energy you get out, how much you put in, needs to be greater than 1. And we see JET, which kind of sat pretty close. JET's record pulses are about 0.67. And then ITER's targeting up here, obviously, of course, a Q of 10. So fusion plants, like fission plants, large fission plants, are quite costly. So ITER first of a kind construction cost is something like 22 billion pounds. And much of that cost, of course, is concrete, but in the case of fusion, we have magnets and lots of steel. The massive material inside ITER is around about 43,000 tons, so equivalent to an aircraft carrier. So we're talking about an awful lot of material. And it's unfortunate that the cost of a device scales proportionally to the square of the magnetic field, the Q of the radius. Well, fusion reactors, the fields are high, and necessarily so to keep the plasma confined, but also we know that the confinement scales well with radius. So you ideally want a big device. So it's an unfortunate truth that the closer you get to success, the more expensive these devices become. So the next set of devices, which might cost tens of billions of pounds, we have to be pretty certain they're going to work and function well first time. So in the next 10 to 20 years, if you do want to deliver fusion power, there are a number of things you have to be aware of, which is, first of all, further experimental tokamaks aren't going to de-risk fusion in that time frame. We now, of course, have the fusion private sector. There's a lot of investors put an awful lot of money in. The question is how shareable will that data be? There could be some really important bits of data that we might not get access to. In terms of the public sector, most of the reactors we talk about, ITER, when I first started my career, was going to start operations, and I think it was meant to be 2019 when it first was proposed in 2000, well, it first signed in 2005, and now the first plasma we care about, the DT plasma, is 2039. And then we talk about delivering STEP in the 2040s, China with CFETR in the 2040s, and KDEMO in the 2040s. So if you really want to do all your design work now, which many people are doing, you're doing so in absence of a lot of evidence. That must be filled with that gap must be filled with simulation. And if you're choosing an aggressive timescale like the 2040s, then simulation simply is needed to fill the gaps for these aggressive timescales. So needing to use simulation to fill in these gaps in knowledge, and ideally transfer knowledge from other domains into fusion where it makes sense to. So a simulation challenge, well, quite simply, is everything, everywhere, all at once. We have the grand challenge of coupled problems. We have radiation, so the neutrons that are produced in the plasma permeate the entire reactor and globally couple the problem together. We have electromagnetism, of course, the magnets themselves produce intense fields. The plasma itself is magnetic, so the combination of those leads to a really interesting EM simulation problem. Dealing with the structural forces and gravity, like I mentioned earlier on, ITER is 43,000 tons. It sits isolated on gravity pads. Simulation of that scale, of that system, as a function of time, is pretty tricky. We have high temperatures. We have chemistry in terms of tritium transport, for example, and all this is coupled in time because, of course, as neutrons are produced, they cause transmutation, which changes the chemical makeup of these materials, and over time these materials become degraded. And of course, it's multiscale. As was mentioned in the previous talk, we have to deal with phenomena that happen at the atomic level. So radiation damage starts at the atomic level, but has a macroscopic impact on the operations of the plant. So how we join these things together, we are working towards what we call a full plant digital twin. Digital twin is one of those very well used buzzwords. So we should probably state precisely what we mean. And what we mean is the definition really put forth by Greaves and Vickers, kind of the originators of digital twin, which is really about a multi-scale, multi-fidelity system that allows us to forward predict in time through simulation. So by basically sticking all the physics together, the hope is out of that will arise the emergent phenomena we need to worry about, the black swans that will cause us problems. So as we think about simulating the entire plant, we have to worry about what's going on in terms of plasma. So we have some very detailed simulations that dictate what goes on in the plasma. Of course, these are some of the most challenging simulations that are done, often involving tens of thousands or hundreds of thousands of CPUs to really evolve our understanding of what goes on in the plasma. We need to worry about how we can then transfer that learning, those high fidelity simulations, into practitioners' hands. So we often use things like Gaussian processors and other machine learning techniques to basically figure out parameter sweeps that train us the right latent space, and then provide those to people to be able to do really rapid simulations. We need to worry about how we stick in multiphysics on the engineering side. So we're busy designing a platform which combines the Moose framework, which was mentioned in the previous talk, with another finite element library called MFEM, which is much more scalable. Doing demonstrations. So for example, we've found we can, with modern tools, we can simulate the entirety of the mechanical behavior of our master upgrade tokamak actually in 3 minutes, just chucking it onto, you know, a few thousand cores. You can actually chunk through the whole system pretty quickly. Bringing that together with crystal plasticity, again mentioned in the previous talk, and also multiscale modeling in terms of how we deal with coupling our different length scales. So by building these demonstrators, which currently sit as kind of isolated things, we want to slowly bring those things together to form more complete simulations, which will hopefully allow for these emergent phenomena to arise. So by using HPC judiciously, we can accelerate a whole range of these simulations. So we can turn around simulations quicker by having much more scalable algorithms. Application on the largest GPU machines available allow us to, again, to go through enough simulations to build this latent space that we need to build our surrogate models, but it also allows us to do things much more quickly in terms of prototyping optimization than you previously would do. Just to give you examples of the use of HPC, so very large, we often call hero run type simulations. If you're imagining simulating an entire reactor, you'll be looking at the hundreds of thousands of CPUs range, or very detailed simulations of reactor subsystems. By throwing problems at the 100 to 10,000 CPU level, you can imagine building simulations that allow to optimize the design of particular components. If you really want to understand what the uncertainty space looks like, then you've got to go much broader in terms of your compute, going into high throughput computing. Just to give you an idea of how big the problems we deal with are, this is the mass problem I spoke about. We think if we added an all singing, all dancing, all physics model, we think we're probably getting somewhere towards about 100 times bigger than what we simulate currently. And then really the sky's the limit. How do we get to ITER, to whole reactors? That's an unknown question. But almost certainly it will be multi-fidelity, because we can't hope to do all the physics at the same length scale. So radiation damage is our kind of one of our grand challenges, is how we then can evolve the structures that arise in our systems from the sort of the nanometer scale with density functional theory, looking at how these can build up into clusters and defect clusters for a single grain, how that intergranular dynamics impacts things, and again, how that manifests at the strongest length scales. So very much like what was mentioned in the previous talk, we are using surrogate models at these lowest length scales by building them from trained sets of simulations, by chucking these problems onto HPC and building through those, and then applying standard machine learning techniques, using things like PyTorch and libtorch to build these things and integrate them into our simulations. AI, of course, is a huge player in this space. One of the biggest CPU drains can be doing large simulations of what goes on in the plasma. So we often need to have a indicator of what's going on, not necessarily the fine details, but indicators at lower length scales and more approximate simulation packages. So we can take these large simulations, again, build reduced order model simulations, machine learning surrogates, which massively speed up their workflows. And similarly, if we want to use machine learning to do reinforcement learning for like controlling the plasma, which is something we're actively interested in, then again, you need a corpus of simulation data to go with this large latent training space to train your AI model on, so it has enough data to try and make the right corrections to control the plasma. This is an actively ongoing project. sitting at the very detailed side of simulation, we're looking at how we can use multi-fidelity approaches again. So this is a one-dimensional map of the cooling circuit of one of our experimental facilities. This is a high fidelity version using turbulence models, and this is a full all singing, all dancing spectral CFD model of the Chimera systems. This is using the full grunt of an exascale machine to model all the turbulence. This is a full DNS simulation of what goes on in the system. The idea is here is we don't trust a lot of these turbulence models when dealing with full fidelity systems. So we need to see if how and when these models break down, and we do so by testing these large-scale models. And then if this is still okay, the question will be, when does it break down between this fidelity and that fidelity? So applying those approaches again, hopefully to allow us to make judicious use of our simulations. Skip those ones. So with that information, hopefully you've seen from these slides, it's actually information, which is what we're after. And a lack of it can completely paralyze your decision making. If you don't take good care of your data, you will not be able to exploit it when you then want to deploy it on broader problems, AI, when you want to build your digital threads or your data lakes. You must really be taking care of your data. Otherwise, the brambles will take over and you'll be left with a whole bunch of technical debt with information that you'd love to be able to use, but can't. So with that, you have to think about what formats you're using, making sure you have openly available specifications so they're more easily ingestible into AI. And for us, with the way we look at these problems is that we try to take all previous information, including from non-fusion domains, and use those to figure out what we can do when we don't have information. So using the last talk as an example, can we apply those models to a priori predict material properties in absence of irradiation? If that's true, then we want to add on the special source that we need for it to work in terms of fusion. And for us, we also take a Bayesian approach, which is thinking about how can the next simulation we do add the most value. So in summary, it's our assertion that HPC AI in the simulation will be a driving force in the delivery of fusion because we simply can't do it any other way. We think there's a huge amount of benefit we can do by passing this information, these skills and these tools to industry, particularly in the uptake of HPC, particularly the engineering sector where Britain does pretty good, but human factors dominate the uptake, in terms of the difficulty of using some of these tools. So there may be some training has to be given out. But this journey that we're on isn't actually that different from other sectors. So similar changes are happening in advanced nuclear systems, in aerospace. And we hope that if these advancements that we make, we can spill to other domains. And again, we take a very collaborative, open approach. So if there's anything here you've liked the sound of and you'd like to work on, then we're very open to that. And we think it's this deployment of digital twins, which will be central to validating our understanding by applying them on systems where we do have a good understanding to then have confidence to move them into a more uncertain domain. And in doing so, we'll hopefully allow computation to be used as the third mode of discovery. So with that, I will stop. Hopefully that's brought us some good questions and hopefully also on time.
I think we're doing okay for time. That's just I'll blame myself for poor hosting. So thank you very much for a really interesting talk, Andy. And so now we've got about 25 minutes for a Q&A session. So we've had a number of questions come in on the Slido. If you have any questions about any of the specifics in the talks, then please add them, or more general talks on data science, nuclear, and some of the things you've heard. And if you have any talks about any questions on the Gene Golding Institute as well, I think some of our colleagues from Gene Golding are staying around as well to answer any questions. So if I go to the Slido, I'll ask the first question at the top of the list. So we've got Mark. So perhaps Mark, if you want to address this first, and then perhaps some of our other speakers can jump in. You mentioned skills requirements. What are the main data science skills challenges for nuclear, and what can universities do to help?
Right. So the main skills challenges. I mean, it's really it falls into two categories. The first one is what I suppose I would call DevOps type skills. That's very IT term. What I mean by that is practically using tools like frameworks, like was in Python, for example, and how you would apply them to engineering problems. That's probably the first one. The second one is just, I suppose, probably more around the familiarization, or perhaps the lack of or the avoidance or removal of fear around the deployment of AI. So familiarization with the technology, familiarization with the risks of the technology, familiarization of the opportunities of the technology. And I think those are probably the biggest areas that, as a group, we've identified as being one of the challenges. In terms of what universities can do to help, I think it's bigger than universities, to be honest. I think it starts really for school is we need really to focus on mathematics and programming skills around AI in particular from a school and beyond. We also need to think about how we would new skill industry. I mentioned around new skilling existing workforces is can we accelerate the adoption of AI either by making it easier to use or by providing training resources to industry users. And I think that's probably two ways the universities could be involved in this. I think also as well, just to say as well, I mean, a couple of the case studies I presented were really aimed about making things easy around AI. And then if there's anything that could be done in the innovation space there, I think that's something that our industry would be very keen to take hold of. Industrial people who work in the industry don't necessarily have time to learn complex tool sets. So is there a way we can make them easier to use? And that's probably something to think about.
Really interesting points there. I'll just open it up to any of our other speakers. If you have any more general comments on skills before I perhaps dive a bit deeper into some of those specific points Mark raised.
Well, I mean, if you're thinking about skills generally, I mean, there's a need for skills across the whole spectrum, from apprentices all the way up to PhDs in the nuclear sector, and keeping on top of that is trying to encourage that is really hard in a challenging funding landscape. Basically, that's the big issue, I think.
Yeah, constant challenge in that aspect, Chris, for sure. So one thing I want to pick up on that Mark said is about making tools easier to use. And Samara, in your talk, you talked about the kind of end-to-end process that you'd adopted. Was there anything specific that you did around the usability of your solution?
Yeah, so other than the sort of like data analysis and data pipeline that we did, so I think I mentioned we connected all the results and all the outputs to Power BI dashboards. So I think that's like an example of like a pretty useful, easy tool to use for everyone across nuclear. But then because that gave that accessibility to like all the relevant people to understand what had been done.
Yeah, that's great. And we use Power BI at the University of Bristol as well. So maybe some of our colleagues can perhaps implement some of those solutions as well and adopt some of these kind of techniques. Okay, so if I move on to one of our next challenges, one of our next questions. So the next one on the list is how are you dealing with data security and AI data challenges in a highly regulated sector? Does anyone want to jump in on that?
I think I could probably jump in on that one. I think the answer is we're working with the regulator. So one thing I didn't mention around working with the regulator is, they want to use AI too. And that's the other side of AI and skills. It's the fact that, we talk about lack of funding and for skills development, that's true. There's also a distinct lack of people. If you look at the skills required in the sector, there isn't enough people in this country or in the world, probably, to be honest, to fill those skills gaps. So we need to think of ways by which we can introduce smarter tools to do things more efficiently, so we can make more out of having less people. And I think, from that perspective, or the regulators are just keen to use AI as anybody within the sector. And I think that's one of the ways by which we can accelerate the adoption of AI, is by establishing that sort of common ground between the regulators and the industry users to drive the benefits for all. That's before we even talking about the improvements on safety, etc. that you could bring for that.
It's a good point to highlight, though, Tom. I mean, on the Sindri Prosperity Partnership, for instance, getting data in a rigorous form is quite that's one of the reasons the Sindri toolbox is not out there just yet. I mean, the EDF systems are very secure. University systems are less secure. There's a disconnect there, and that has to be addressed to keep everyone on message. Different companies have slightly different data storage or whatever, facilities, and getting those to talk to each other is hard. So it's right at the top of the agenda, I would say, to move this forward, with no answer just yet, but there's a willingness to get there.
Yeah, sure. And Andy, perhaps from a fusion perspective, obviously, well, people on the call may not know that fusion's regulated slightly differently than fission. So you're reporting in through a different route. Is this a common challenge that you see in terms of the data security aspect and challenges around that?
We've not really had the discussion actually yet with the regulator, because the operation of fusion plants today are all done through the exact same regulator, through the Environment Agency and HSE. It's a different risk profile and a different appetite for change, I think, which I think makes it a lot easier. But we have active ongoing projects internally on deploying AI on a vast range of things, from piling many scientific reports into it so you don't do the same research more than once, things like that. So I think for us it's a little easier, but as Mark mentioned, there's also it feels sometimes like AI is a bit of a boogeyman for people, when they don't quite realize what's going on and how it works and the security involved. And so there's a bit of a stigma to overcome with I forget the word Mark used, but I'm going to say sort of the SMT.
Yeah, that's great. So we've had another question in that links a bit to what we've talked about there, about the kind of data specifications, and if you're using sort of any common standards, or if there's nuclear specific data aspects that you're considering, or if you're adopting things from other sectors. I don't suppose anyone's got any thoughts on that as well.
I can say a few things. So there are many issues associated with the ingestion of PDF documents, right? Despite the fact that you can easily dump a PDF into a ChatGPT instance and say, tell me about this document, you're assuming that it can read it correctly. But actually PDFs are for printing, they aren't for reading, right, of data. So if you, for example, as an experiment, open up any PDF document and try and grab all the text in something complicated, sometimes you'll find out you're actually bringing in bits of the document you weren't expecting. And so when it's ingested, it might be in the wrong order. So we don't think about how the AI actually ingests this data. And so we worry about, or some of the things I worry about, is actually making sure this data is being ingested correctly. So one of the ways to do that is to use openly defined standards, which PDF isn't, by the way. But I believe the government even mandates, the government has an open first process that says you should always go for open standards where possible. So things like ODT files, for example, if you can specify those, then you'll actually have an ODT reader, which is more easy for the AI to ingest, things like that.
Yeah, we've discussed standards within the AI4Nuclear group, and I'm sure it's a subtopic we're going to be revisiting time again. It's a very controversial topic. I mean, they can be useful in some instances, but they can't replace, and they should never replace, collaboration. And really, what's most important is collaboration, rather than the specific standards. Standards are really there to help with reproducibility. They're not really there to help you deliver something in the first place. So we do need to find better ways of collaborating across across sectors and within the sector to really accelerate the growth of AI and nuclear. That sounds like something I generated from AI, but yes, I think that's really important.
Yeah, great. And so building on that theme of collaboration, a few of you mentioned interdisciplinary kind of research, interdisciplinary input. How has your work or research benefited, or how could it benefit from this kind of interdisciplinary aspect?
Well, for me personally, I think fusion is the summation of most other disciplines, or many other disciplines. So very much we see that we want to pull in as much knowledge from outside to give us the biggest sort of head start. We don't want to solve problems that are already solved, and if people are already working on solving them, we'd rather work with them than come up with competing solutions. So for us, very definitely, it's huge for us.
I mean, I could cut from what I talked about, Tom. We've sort of identified that the way forward is probably not involving so much material scientists and mechanical engineers. It's more about the software engineers that bind it all together to make it actually work, is where we need a bit of a boost of an input. So you need those two camps really working hand in hand together. And traditionally they haven't, but you need that to push things forward.
Yeah, I think one of the things we've learned from the sector is sort of, I mean, there's sort of two ways really. I mean, the first is ideas about sort of where we could apply artificial intelligence that we might not have thought of before, and we've had some really good case studies. I mean, there was a company that's funny enough just based up the road from where I work who gave an excellent presentation on the deployment of AI-based solutions for detecting faults on the rail network from trains, and that was really inspirational. That also gives us an idea of how the technology can be used, but it's also the second part of it is it inspirational. When you see these case studies being applied, it helps to overcome the kind of reluctance for the sector to actually try these things, because once nuclear has a reputation which enforces itself about being very conservative and risk averse, but actually when we see the risk balance case, we're actually very quick to adopt new technologies, or can be very quick to adopt new technologies, and we can see that in some instances. I mean, as an example, when we had our first meeting on AI4Nuclear, we had over 15 case studies where people were already using artificial intelligence for nuclear problems, because we didn't think when we actually opened it up, we didn't think we weren't even sure we were going to get any. And so it was quite, so we all said, okay, well, we're already doing AI, really. It's a question of now, how do we manage that going forward? So yeah, I think they're the two areas for me.
Yeah, really interesting. And Samara, obviously the example that you presented today was highly interdisciplinary. Well, I would consider it, with aspects of climate science, sensors, Internet of Things, data challenges. Is that something that you're routinely doing, taking these different kind of interdisciplinary themes and bringing them together?
Yeah, so that is mostly what we do, really. So most of our work is within the nuclear sector. There's been multiple case scenarios when we built data pipelines for example, for a farm, for example, just to then assess the health of some farm fields. So they had some data that need to be collected, and then that was put through some image sort of assessment to define the health of the crops.
Yeah, great. That's totally different.
Yeah.
Really diverse.
Yeah, exactly.
But the same sort of data principles are in place. Great. So I'll kind of change tack a little bit. And so Andy, I think this question might be addressed at you, but I'd be keen to hear everyone else's thoughts as well. Do you think AI, machine learning and simulations will reduce the need for physical experiments, or does it allow you to get more out of them?
I think both. I think it will allow you to get much more from your experimental campaigns by actually investigating parts of the parameter space that you haven't looked at. So certainly for high dimensional problems, figuring out the next most interesting simulation is really difficult for humans because we can't think in 12 dimensions, or so that certainly I think will help. But also, I do think that when we start looking at simulation differently, and stop relying upon kind of textbook values and can move to more holistic first principles driven approaches, where you can apply V and V on the same problem over and over again rather than revalidating. I think engineers view validation through a lens of, oh well, we've got to validate it by building a test rig. Well, do you? Have Maxwell's laws changed and solid mechanics is still true, and we know how temperature works? Do you actually need to build a test rig? So I think more targeted testing, I think, will be what we'll see more of. I see Mark nodding, which is really reassuring, so I'm less nervous now.
I'm going to say I agree with you, and I'm going to say it in my very Mark way. I think it's both. I agree with Andrew completely. It's both, but really you'll probably end up doing more experiments. You'll do more experiments because they'll be more valuable, and you'll do less rubbish ones. You do a lot of rubbish experiments in industry, but Andrew described it a bit better than I did there, but yes.
I mean, I've got nothing more. I agree with what Andy and Mark have just said, Tom. I mean, ultimately the only truth is the experiment. You need them somewhere in the chain, but yeah, more data. It will help focus at the correct experimental test matrix and things, and make us think more about which tests are really needed, because there are some. I don't know what the word is. I didn't want to say junk, but there's a lot of tests undertaken without due diligence thought going in, and they're very expensive to do.
Yeah.
Really interesting stuff. Okay, so I'll come, in the interest of time, I'll come on to the final question. So I think lots of really interesting ideas, lots of really interesting thoughts that we presented today, and I'm hoping that people on the call have been inspired to think about nuclear when they're thinking about data science. So what can people do if they're interested to get into the sector? Have you got any suggestions that people can adopt or ways in to get involved?
I have several PhDs available at the moment, Tom. I'm sure that's not quite what you meant. There's a lot of opportunity at the moment. I mean, I think if you sort of slightly rephrase what you ask, if you could talk to someone a bit more junior, I think a career in nuclear is a great thing to go into with lots of opportunities at the moment. So that would be a rather weak answer to your question, but that would be how I phrase it.
No, thanks, Chris.
Yeah, sorry, Tom. If I say something, I think me myself in a pretty early point of my career, and I think one of the things that are most exciting in the data science world and in nuclear is the fact that it's still, even though we've seen all these case studies and it's great, it's still very early on. And there's still like huge opportunities from data transformation to more like complex tools like machine learning. So I think that could be like a really good, for me, like it's a really great inspiration to sort of like carry on doing the work we're doing.
Yeah, I'll just echo the comments. Really, it is a good time, and there are lots of opportunities. I mean, I'll say join AI4Nuclear because the other side of AI4Nuclear is good for networking, and there are opportunities within the sector. People are looking for solutions to come and present your ideas. Perhaps you've already got some case studies from other sectors or from your research. And try the industry out. There's a lot of excitement around AI, so there'll be a lot of interest in bringing AI technologies into the industry. But there's also lots of skepticism as well, so there's a bit to overcome. So you'll have to have a bit of perseverance to get through that, and perhaps work with others to help you do that. But I think that's the way to do it. You know, just there's lots of opportunity now. Now is the time to get out there and talk to the industry.
Great. And Andrew, any final comments from you?
I would say the best time to learn it is tomorrow. Second best time is probably now. And there's a whole wealth of training data out there. You know, a wealth of training courses you can do, little websites people put up to show demonstrations have got. So just give it a go.
Great. No, a really good way to end, I think, on what I've really enjoyed, really inspirational, exciting, lots of different ways to get involved and lots of different data science challenges. So I'd like to take this opportunity to thank all of our speakers. So we've got Mark, Samara, Chris and Andrew. Thank you very much for your time, and Patricia as well for introducing the Gene Golding Institute. I recommend everyone on the call to have a look at some of the other events that are happening this week. We've had a few links in the chat to an event tomorrow evening, which will be kind of a bit of a flagship, my understanding is, from the whole data science week. So there's lots of opportunities to get involved. If you're interested in nuclear specific opportunities, then please feel free to reach out to the Southwest Nuclear Hub. Myself and my colleagues will be happy to assist, make introductions into the sector, as Mark has said, and really help build those links and opportunities. So I'd just like to say thanks again for attending. I hope you've enjoyed this session. Thanks again to our speakers and to the Gene Golding Institute. Oh, Patricia, I thought you wanted to say something there, but yeah. Just thanking everyone again. So all the best, and try and get involved in some of the other events if you can this week.
Thank you.
Thanks.
Thank you.
Bye.